Hello again, this is Reimer Fochler from AKG Acoustics speaking to you from the head office in Vienna. Welcome back to the second chapter of my online training, Wireless Basics Part 1. In the first chapter you heard already about the radio wave spectrum and the nature of electromagnetic waves. This time I want to talk about the behavior of a radio signal when propagating through space and the handicaps we have to consider when using wireless technology. So let's start with an analogy from a real-life example. Let me take this picture of a billiard table to explain the chances for a radio signal to travel from a transmitter to a receiver and what all could inhibit this to be completed successfully. Let's pretend that the white ball is our transmitter and the red one would be our receiver, and we want the signal to travel the shortest possible way. We will notice that the direct path is not possible because a blocking object is in its way. That could be a metal construction like an iron curtain in a theater, a metal door or such. If we would take the indirect path, the signal will be reflected in many directions by surrounding surfaces like ceilings or walls. Some portions of the signal will even be absorbed by an absorbing material and will lose its strength to travel on. Audience, for example, is a very good absorber. In the end, only one path is leading to the target, where the signal is reflected from surrounding surface, finding its way to the receiver. In fact, these propagation characteristics are a law of nature, and we can encounter them in many situations of everyday's life. When a wave propagates in space, it will be impaired on its travel by a few fundamental physical phenomena. Reflection. We understand reflection as a change in direction of a wavefront at an interface between two different media, so that the wavefront returns into the medium from which it originated. Refraction or diffraction is the change of direction of a wave in passing from one medium into another. Absorption is the reduction of the intensity of any form of radiated energy as a result of energy conversion in a medium. And scattering is the process in which a wave is diffused by collisions with particles of the medium that it traverses. Mesh wire, for example, would be a very good diffractor of a RF wave. But all these handicaps are important to take into account when placing antennas, for example. We have all seen some of the propagation handicaps in real life before. Like here on the first picture, a laser beam is reflected from a hard reflective surface in a perpendicular angle. Or a drinking straw looks broken due to the light waves breaking when traveling from the air into water. That's what we call refraction. And diffraction is when the wavefronts are propagating in the open field and then they are bent around sharp objects when traveling through them. Mesh wire is a good example for diffracting radio waves. Let's have a look on a situation that we all might know. We have a reflective surface, like a blackboard with a presenter speaking in front of it. The wireless microphone is transmitting its radio signal in all directions, trying to find their way to the receiving antennas. If the antennas are positioned in the back of the stage, they are hidden behind the blackboard, and this way most of the radiated signal will be reflected to the front of the room, reducing the chance of continuous reception at the receiving antennas. So much better if we place the antennas in the front, and so the antennas are in direct line of sight with the transmitter. That way we have the best conditions to establish reliable reception. Another example. This one is showing a presumed theater stage where the scenery with edged buildings and reflective surfaces. As we heard that waves are bending around sharp obstacles, it is not the best idea to place the antennas above those buildings on top of the scenery, but again, better to choose a position in direct line of sight of the transmitter, and therefore help to maintain a strong uninfluenced radio signal reception. Here we have a very common example of a not so ideal antenna position. Since water is a very good absorber for electromagnetic waves, the human body attenuates the radio wave significantly. Nevertheless, engineers tend to place the antennas close to the front of house position, and this way the radio waves have to pass all the absorbing bodies while the signal gets degraded on their way from transmitter to antenna. So in that situation it would be much better to place the antenna close to the stage, where the signal is again in direct line of sight to the transmitter. What is also seen quite often is that antennas are placed in the light rigs of a stage setup. What is common practice appears not to be the best solution if you consider that the metal construction with all its angles and windings is scattering the radio wave, and that way it's producing diffuse reflections that are weakening the signal strength by increasing the chance of multipass cancellation. We will hear about multipass cancellation a little later, but if antennas are placed at the side of the stage, the signal can travel unobstructed on line of sight from the transmitter to the antennas. In outdoor applications, even fog can scatter the radio wave to a certain extent. Thinking about all these tiny water particles that are diffusing and scattering a radio wave. Okay, that was a little bit for the understanding of how a radio wave propagates through space and what can disturb a wave in traveling to the receiver, respective to the antenna of a receiver. I was using the artwork for the last 4 slides by the courtesy of my little daughter, hoping that it was easier for you to visualize these basic principles that are still important to take into account when setting up a wireless microphone channel. Next time more on radio signal basics. Thank you for your interest. Stay well, stay in tune. Reimer Fochler from AKG Acoustic.